This is the second video in the gravitation topic, and in this video we'll be looking at Newton's law. So sometime around 1986, Newton formulated and published his law of universal gravitation. And prior to him publishing that, it had been thought that gravity was a concept or a force unique to Earth. And Newton's law of gravitation not only explained why things on Earth will always fall down, but also explained the motion of celestial bodies, and I'm quoting Newton himself there. However, Newton's theory had a couple of problems. The first of those was instantaneous action at a distance. So Newton himself couldn't understand how it was possible that some force could act instantaneously at a distance of several light years and further, when the limit of the signal propagation throughout the universe is the speed of light. There was also the problem of how it actually acted at such large distances. And then in 1859, so some 200 years after Newton developed his law, new observations allowed astronomers to see that planetary orbits shifted over time. So this is termed the precession of the perihelion. And what that means is the planet doesn't follow exactly the same path in every orbit around the sun. That path shifts very slightly on each orbit, and it means that over time, the planet's orbits trace out a pattern as you see on the screen, so something like a flower. And Newton's laws didn't allow for that. And the final problem, it was very inaccurate when it predicted the magnitude of something called gravitational lensing. So if we have a look at this picture, we have a beautiful galaxy sitting on one side of, for example, our sun, and we have us on the other side of the sun. And what we expect to happen is that the sun blocks all the light from that galaxy and we don't see anything. However, what actually happens is that the gravitational field of the sun directs the light from that galaxy around the sun, and so we can still see it. So this phenomenon is particularly observable to us during something like a solar eclipse, where the moon is in principle blocking the entire sun, and yet we can still see some of the light rays from the sun coming around the edge of the moon, giving it a beautiful halo. One of the more impressive manifestations of gravitational lensing is something called Einstein's ring, or an Einstein ring. And there's a beautiful example here where we can see that due to the gravitational field of what I believe is a distant galaxy, light from the galaxy and stars behind it has been bent around it, and we see this lovely feature of a ring around a star, or ring around a galaxy. In 1915, Einstein came up with his theory of general relativity. And what that is essentially a better way of describing gravity. So Einstein's theory of general relativity solves most of the problems that Newton had. And predictions made by Einstein's theory have been proven time and time again. One of the first proofs of Einstein's general relativity was a much more accurate prediction of the magnitude of gravitational lensing, hence why that lovely image is known as an Einstein ring. So Newton's theories are valid under certain conditions, and they're conditions that were observable when Newton was developing his theory. So they're valid when the speed of the object we're interested in is much, much less than the speed of light, and also when the gravitational field, or the gravitational potential, is much, much less than the speed of light squared. Whereas Einstein's theory at the moment is valid so far in all the conditions it's been applied. But I should point out that it's still being tested and probed and prodded, and that it wasn't until some 200 or 300 years after Newton developed his theory that any flaws were found with it, that any concrete flaws were found with it. And so it may be that we will find some flaws in Einstein's theory as we get better and better technology that we can make better and better observations with. So as I said, Newton's theory is valid for objects travelling at low velocities and for weaker gravitational potentials. Another way of defining a weak gravitational potential is something where the masses are particle-like relative to each other. So where the radii of each of the masses are involved are much less than the distances between them. And when this is the case, then Newton's law of gravitation states that the force of gravitation is equal to gmm on r squared. So where the capital M is the first mass, the little m is the second mass, and r is the distance between the two masses. And g is the gravitational constant, which is equal to 6.67 times 10 to the minus 11 meters cubed per kilogram seconds squared. Excuse the subscript. So that's quite small. And the strange units are what is required to give the force of gravity the units of newtons. The force of gravity is the attractive force between those two masses. So what happens in the case where we have more than two masses interacting? So say this case where we have large mass 1 and two smaller masses m2 and m3. How would we calculate the force due to gravity on mass 1? And the answer is that gravity is very nice and it obeys the principle of superposition. That means, for example, when we have two masses acting on a third one, the force due to gravity on that third mass is simply equal to the sum of the force from the first mass plus the force from the second mass. And again, I apologize for the subscripts. They should be unit vectors in the direction r1 and r2. You will note that this is a two-dimensional vector equation, so you are more than capable of solving the problem. And that is it for Newton's laws of gravitation.